The guys are up and running. They gave me thumbs up. So the next two speakers, Rudy and Henry. Well, Rudolfs, I was his supervisor for the master's thesis, and with Henry, well, he's doing his PhD, and I'm supervising him partially. I'm not his primary supervisor, but advisor. So let's see what you guys can tell about the industrial control systems. There you go. The floor is yours.
Cheers, Bibi. Hello, everyone. I'm happy that we started earlier. Well, we'll try to be quick so we can all get to lunch a bit sooner. Our talk is on detecting threats on industrial and automation control system networks. So a bit about us. I'm Rudolfs, or Rudy. I work at CERT.LV, incident response, and as Bibi mentioned, he was my supervisor in Tallinn in Estonia. And that's where I got to study this topic.
Yeah, so my name is Heinrihs Skrodelis. I'm a PhD student at the Riga Technical University. I'm studying computer science, and my research interests include cybersecurity and data science.
Okay, moving on. So, just a short outline of the talk. I'll be covering this first part, which is, I'll start off with some background and context information on the actual ICS, IACS, and all that, and then let me just get a pointer. Yes, then I'll cover a bit about what actually is an industrial and automation control system and its network, and then I'll delve into a bit about the protocol that I looked at, and then moving on, some real-world attacks that happened a while ago and not so long ago, and then finally into the actual prototype development and some demo as well. Okay, so context. So the overarching goal is for CERT.LV to develop a operational technology network intrusion detection system, yes, aka a sensor. Pretty much, we all are familiar with some kind of an IT sensor. Suricata, for example, and it shows you alerts if something's bad is happening. But regarding the OT world, or operational technology networks, it's a bit harsher environment. The terrain is not so well understood, and as such, a lot of research needs to be done. And this, the prototype developed is a small step towards the final goal of developing such sensor. Now, the sensor would be used in production environments in the energy sector, mostly electricity, and it is possible because of the laboratory located at CERT.LV. This laboratory is IACS laboratory. As you can see in the picture, there's a few red rectangles, and there's this control station right here, which is just the computer that lives on this network. This is the SCADA lab that I experimented on, and that will be used later on as well. And just a short overview of the contents. Pretty much each red box has mimics different parts of Latvian energy sector. For example, this 4.1 box, it mimics the workings of electrical substations. So, for example, a city may have its own control station, and then the box is here. This is a remote terminal unit. It would then control the electricity flow to some of the households. And the boxes, the other two red boxes over here, they're also related to electricity. And the top part is more towards gas transmission as well as energy production. The lab is currently being improved, so it looks quite different now, but that's the basics. Yes. So a bit of background. I don't know, how many do people know what ICS, SCADA, all that? Okay, I see some nodding. Just an overview. So ICS, Industrial Control System, IACS, Industrial Automation Control System, and SCADA is supervisory control and data acquisition. Now this picture on the right side, this whole thing is a industrial automation and control system, and in it you have this SCADA server. It has a lot of parts. I'll just highlight the important bits. Now the SCADA server serves as a controller, like from a higher level. Humans can interact with it, some employees, and then the employees then issue commands, which are then sent to these boxes right here, which are called remote terminal units, which then forward these commands to programmable logical controllers, or PLCs. You can see two here, which then actually connect to industrial equipment. In this case, it's some kind of a, I guess, oil thing, but regards to the prototype that was developed, here it would be some electrical components, like switches, for example. And then remote terminal units can also read data just from a sensor. Yes. Now regarding the security, I think this is well understood that it's part of critical infrastructure. Obviously, we need to spend a lot of time to protect it, to segment this network, to not allow any wrongdoings to it. Since all of us currently, this whole building is controlled by some kind of an IACS or SCADA system. And for that, of course, there are devastating consequences if there were any attacks. Okay, moving on. Yes, so this SCADA server communicates with RTUs using a protocol, different kinds of protocols, but in our case, we look at just one protocol for this prototype, and the protocol is IEC 60870-5-104 or IEC 104 protocol. Now, this protocol is specifically designed for telecontrol of these electrical substations. It sits on top of TCP, so you have all the sessions, and uses port 2404. Now, since it uses TCP, it also sits on top of the IP stack, and it requires an IP address of the RTU, remote terminal unit, to work, as well as a bit more detailed information to reach the appropriate bit for the device. Here I have just a quick picture overview. So there are two types of packets for the protocol. One on the left side, this is just a fixed length packet. So you have two start bytes, and then you have control fields, and then you have, which is not that interesting from a security perspective, but then on the right side you have with a variable length, and you have this bit right here. It's called an ASDU, or Application Service Data Unit, which carries the actual information to and from the RTU. And yes, it doesn't have any built-in security measures. I'll cover that in a bit. Okay, so past attacks. December 17, 2016, in Kyiv, Ukraine, they suffered an attack labeled crash override by security firm Dragos. A large part of Kyiv were left without power for roughly an hour. Now, the attack happened in multiple stages. Attackers got access to the IT network. From then, they established persistence and then pivoted to the OT network via, I believe it was a data historian that was basically misplaced. Now, the malware that was developed and executed, it enumerated the OT network and changed the state of the information object addresses to open and close, which basically meant that they opened and closed circuit breakers, thus changing the flow of electricity. Now, I have some screenshots here. On the left side, you see a extracept of a DLL. You can see an IP address that was targeted, the targeted port log file, and at some part of it, there will also be the IOA, so information object address. And here you can see the actual packet that was seen in the attack, well, not in the attack, but the mimicked attack. So the malware used, this is the traffic from the malware. And here I've cropped out the most important bit. You can see that the protocol used is the IEC 104, and it used this, this bit right here, this information object, which is called single command. And it used the IOA address of 10. Now this is 2016. There was also another type of malware discovered in December 2021. It wasn't part of an attack, but this this malware was found. Someone uploaded the malware to some VirusTotal or Mandiant, or we don't know where, but it was uploaded, and from there it was analyzed. And it pretty much did the same thing. It delivered single or double commands. So these single, this CSCNA1 and CDCNA1. Okay, so the goal pretty much is to have another layer of security in this part of the OT network. So attackers compromise the IT network, they establish persistence, then they access the OT network. So we need something in the OT network that could see these malicious, potentially malicious commands. That leads us to the work of the research. It's the operational technology intrusion detection system. Now, here I have a simplified graphic of an OT network where there's a SCADA workstation from which an operator can send a command to an RTU, remote terminal unit, and then the command is forwarded to PLCs, which then execute the command or report back some data. Now, this part here, as I mentioned in the overview section, is used by, the command is sent using the IEC 104 protocol, and it's mostly insecure. It's unencrypted. There are no built-in authorization mechanisms, as well as, yeah, and that leads the security up to the vendors who create devices that use this protocol. So the vendors can implement it however they please. That's one part. The other part is that the actual engineers that use the systems, that build the systems, they have to turn the feature on and stuff. Of course, there are some caveats. Yeah, so there are some issues with this. Hence, the goal is to place an intrusion detection system that can either detect, prevent, notify, etc. Okay, so on the next slide, I'm going to zoom in on this intrusion detection system. So if we zoom in, now I'm dwelling into the actual prototype that was developed. It was developed using Zeek. Zeek, I'm sure people know what Zeek is. It's a network analysis software. So here is the actual system, and the blue boxes are the actual files that Zeek uses to analyze traffic and perform actions. So if we see some traffic coming in from the SCADA control station, gets split into packets, and then the first thing that happens is a plugin for Zeek called Spicy. It's pretty much a C++ language wrapper. So it is easier to write a C++. The Spicy plugin sees whether the traffic is for IEC 104. If it is, the traffic gets forwarded to the interface definition file, or the glue file, I like to call it, which creates events. Yes, creates events, and these events then finally can be processed by the Zeek script file here, which performs some action. So it's the most important file in this context. In the prototype's case, it logs the traffic, nothing too special, but it can also be leveraged to block it or alert the operators via some CM system or something else. Okay, so now I'll cover a bit more on what the actual protocol is looking for. This is an extracept of the packet that I showed before. There were variable length packets and fixed length. This is the variable length, and you can see here this is the application service data unit packet. And here's the important bits, pretty much. There are 3 types of packets. This is the I format packet. The SNU format doesn't really matter that much. So this is the I format packets, and in the packet you have either one object or multiple. It varies, but in our case, I've highlighted just one object, and it contains 3 parts. Information object address, IOA. It was seen also in the malware sample before. And it also contains the information elements, which are information object codes, or just object codes. So in the prototype's case, it looks at two of them, which were seen in the wild, because they were seen in the wild. So CSCNA1 and CDCNA1. Single command and double command, respectively. So pretty much, we get an IEC 104 packet. Is it ASDU? Yes. Is it one of the commands that performs an action? Yes. We log the command and the connection details. Now, to actually test the prototype, I ran an experiment with a following threat scenario. The threat scenario was that the attacker had access to the OT network and could communicate with the actual remote terminal units. Actions to accomplish this are not easy, not trivial. The attacker needs to be either very lucky or sophisticated. I've drafted the possible chain of events. So, for example, the attacker could gain access to the IT network, similar to the malware that I showed before. Supply chain attack, phishing, you name it. And then attacker needs to pivot to the OT network. So this could happen in numerous ways, one of which could be the data historian, which is used to store data, could be placed on the IT network instead of the OT network, or it could be because of network segmentation issues. Yes, so that attacker would need to pivot to the OT network, and finally the attacker would need to actually see the traffic, 1, and 2, be able to send commands to the remote terminal unit using their own machine. Yeah, that's an important bit. So if the attacker has access to the actual workstation used by engineers, it's game over pretty much. But if the attacker uses their own machine with a rogue IP, there's some hope of catching it. I mean, you can hypothesize that if the workstation operates at weird times, then we know it's an attacker, but that's out of scope for this talk. Okay, so enough with the slides. I'll show you how this actually works on just the terminal this time. But the point of the demo is just to showcase the Zeek files and to show how to add more capabilities to the actual prototype, or to the actual to the actual script. So let's see. So I'm connected to a box. It doesn't matter where it is, but I have 2 folders here, 1 and 2. You can see them here, both of which contain files necessary for the Spicy engine and Zeek to work. Now the second folder is with already adjusted parameters. I did not want to do it on the fly because I believe demo gods would punish me. But either way, let's look at some of the files and I'll just glance over them. So first off, the spicy file, which is the one needed to understand the traffic. It's a lot of lines. I'm not going to go too deep into it, but I'll show a few important parts, one of which is here. It's called the single command. So here I'm specifying the single command that we saw before in the malware. So if Spicy sees the single command, it logs the information object address, and it also logs the single command bits as well. Now, that's the single command here, and if we scroll down, here's the double command. Very similar. So that's the Spicy file. Next up, it's the EVT file or the glue file. Very short, nothing too major in here. So yes, it uses the Spicy analyzer over TCP, 2404 port. And here you can see these two lines where it uses the single command, and it actually creates that event that I was talking before about, which then can be logged by Zeek. So two events here, single and double command. And finally, we go to the Zeek script file, which is also not so long since it's just a prototype. But the most important bits of it is that here it logs the single command, and here it logs the double command. Yes. So, and to actually run it, whoops. So since I do not have, we're just going to read we're going to read that experimental data that I showed on the presentation. And to run it, okay, it's not, okay, whatever. So we just say Zeek, oh wait, I need to go into the first directory. We say Zeek, we say ignore checksums and read a file. And the file we're reading is pcaps experimental data. And then we need to also specify the Zeek script file. And we also need to specify this 1.hlto file. This file is just a compiled file. So Zeek and this file is created using this EVT file and the Spicy file. Basically, it's just a binary file, so Zeek Engine can read the data. And then we launch it. And yeah, as you can see, we saw some files appearing here. The conlog, that's people who know Zeek know that that's default. And the I104 log appeared here. And in it, I know it's a bit difficult to read, but the important bit is that we see the originating IP addresses. And we also see the commands. So we see that a command was sent saying turn off, and a command was sent also saying turn on. And another bit is we can see different IPs. So this is a 10.10.0.100 IP, which in the experiment was the official SCADA, not official, but the legit SCADA station. And this 10.10.0.240 is a rogue machine performing these actions. Now this is I presented an overview of the file, the Zeek engine. Now in the second directory, let me just close all these files. In the second directory, we have the same situation. The Spicy file is exactly the same, but it has an additional line here on the EVT file where it reads another command called interrogation command. Now I'll just open up the first so you can see the difference. Yes, so this is the second file. We see that here it's just commented out. Now if we perform, and then the Zeek script file has an extra few lines to log that event. And to actually launch it, we perform the same actions. So we tell Zeek to, what's going on? Why is it like that? Okay, I don't know what happened. But anyways, we say Zeek, hey Zeek, read read the PCAP file using the Zeek script file and using the binary file compiled with the SPICY file and the interface definition file. We run it, and we see some log files popping up here on the second directory, and a couple more events. In the last line, I believe we had 8. Here we have 14, which makes sense because there's 6 lines specifying the qualifier of interrogation. Now, in terms of security and usefulness of this, actually logging this command is debatable. But wanted to show this just to showcase how it would actually work. Now, in a real-life environment, the Zeek script would be placed onto a live machine and run on some network interface that would see the actual traffic. And then this qualifier of interrogation, it pretty much means whenever the IOC 104 protocol starts a new communication, for example, after rebooting a device, it sends these commands, as well as before a single or double command is executed. Yes, so that was an overview of the Zeek engine, and I'm going to give it back to Henrik now to talk about future plans. Wait.
Okay, so thank you, Rudy. I'm going to now continue with the relatively short theoretical presentation on how we are continuing this this research by elaborating machine learning on it. So I'm going to briefly explain how are we generating threat scenarios, how we are creating labeled dataset, what kind of tools and frameworks are we using, and how are we going to incorporate machine learning in all of this. So since organizations usually do not share their network traffic data to external parties, it's always been a challenge in the scientific community to work on network security solutions, especially machine learning based ones, which highly relies on big quantities of data, quality data, but thankfully I've had this opportunity to work on the CERT.LV, so data and experimenting isn't a problem anymore. So the main objective, or let's say end goal of this research is, of course, the enhancement of CERT.LV monitoring and incident response capabilities. To achieve this, we are creating an IDS that would utilize machine learning model. In order to create a machine learning model, a labeled dataset is needed. And in order to ensure that the data used for model training is meaningful, a comprehensive threat scenario is needed. So the first step before creating a machine learning model is the attack scenario generation. And the threat scenario is being crafted by analyzing previous attacks targeted to both specific protocols and more generic ones. A lot of scientific literature and security company reports are being analyzed, and then corresponding attack vectors are being described with the help of MITRE ATT&CK framework, but I will get into that in the next slide. Also, cybersecurity experts are engaged in this process to review and validate the scenarios, and based on the feedback they are giving, we are adjusting them, and then it's time for attack simulation. The scenarios are being, let's say, executed, and for now it has been mostly done with some Python scripts, but we are also actively researching other tools such as MITRE Caldera, but I will get into that in the next slides. So I'm sure most of you are already familiar with MITRE ATT&CK framework, but for those who aren't, then MITRE ATT&CK is a curated knowledge base and model for cyber adversary behavior, reflecting the various phases of an adversary's attack lifecycle and the platforms they are known to target. And so, as we all know, cyber attacks are rarely as simple structured as they're often portrayed in the media. And in the context of this research, MITRE ATT&CK framework plays quite a big role because it not only provides a clear overview of multi-layered attacks, but also enhances the research replicability and credibility. So here is just a simple example of a threat scenario. Rudolfs already just presented the main details of the industry attack, but this is just an example how we are untangling the attacks with the help of MITRE ATT&CK framework. So in each scenario, we add description and the corresponding techniques from MITRE attacks. And also in the context of this research, we are ignoring the initial access stage because we are assuming that the attacker has already established a position in the network and starts from there. Here's the same attack, but the techniques used are visualized with the blue color, and here it's quite easy to see how complicated the attacks usually are, and here you can see that almost half of the techniques from MITRE framework were used in this specific attack. Also, MITRE Caldera, very interesting tool that is worth mentioning. It's a cybersecurity platform designed to easily automate adversary emulation, assist manual red teams, and automate incident response. And it's built of the previously mentioned MITRE ATT&CK framework. It's available on GitHub, and everyone can install it and assess their security solutions in various platforms. But in the context of our research, we are actively exploring its potential for conducting attack simulations, and this is particularly promising because of the recent introduction of the Caldera OT plugin, which would simplify and let's say enhance the flexibility of attack generation. But since it now only supports BACnet, Modbus, and DNP3 protocols, we are currently more focusing on IEC 104. We haven't done any serious experiments yet. So, and lastly, machine learning. Unfortunately, no ChatGPT here, but machine learning can be used to detect either known attacks or not known attacks if the model has been sufficiently trained. We are putting a lot of work into preparing everything as accurately as possible in order to reduce false alarms and to increase detection rate. And identifying the most important network traffic features is a very important aspect, as it allows to reduce the complexity of the models, and that saves us computational resources and also serves as a safeguard against the model overfitting, which can then lead to generalization of the results. And since we are getting a full network capture with the network headers and packet payloads, there are a lot of data stored, and this aspect is very crucial. We are transforming the PCAP files into CSV files with the CIC flow meter, also a tool available on GitHub, and one network flow contains 84 features, so you can imagine how big the files look like and what it means for machine learning in terms of computational resources. So one question that we are exploring is what kind of machine learning techniques to use. So in traditional machine learning, we typically work with data organized in a grid-like structure. And in this structure, each row represents different things, such as pixel values and images or words forming sentences. And machine learning algorithms process these rows of data by learning patterns that span across the entire data set. And so, unlike traditional machine learning technique, where each event is seen as a separate piece of information based on its features, in graph data, everything is connected. And in cybersecurity, there are usually multiple interacting entities, and graph data captures these relationships, while traditional machine learning tends to treat each event in some kind of isolation. And there are a few publications where scientists play around the graph AI and network traffic anomalies. And this technique shows some promising results because by adding a context to data, it can boost the performance of machine learning algorithms, theoretically. And that concludes our presentation. Hope you have so many questions.
All right, first the applause to the speakers. So I will kick off the question. I mean, context is very crucial, and this will go to both of you from the different perspective. Rudy is dealing with Zeek, and you will be throwing the machine language learning at the problem as well. Now, context, because Rudy, you're detecting the on and off, right? In the IEC 104 packet. However, you do not necessarily know if it's a malicious packet or not. How would you derive if it's malicious or not from your standpoint with the Zeek and analysis of the packets? And also the same will apply to Henry as well about the trying to figure out, especially when you're using the unsupervised machine learning, how do you teach that it's a malicious or not malicious? Rudy.
Yeah, I can start. So couple of ways. One of which is just to look at the source. So in the experiments, the threat scenario was such that an attacker used their own machine. So different IP address was used, and there are other different ways of specifying this. So this would be a rule-based approach. Some other rules might be different off hours when these commands are issued. This would depend heavily on the actual network. So the network engineers. So I don't think a solution can be applied to all sensors that could be placed somewhere. It would need to be adjusted per network.
I see. Right.
Well, about machine learning, well, we are using actually supervised machine learning algorithms. So we are saying which packet is malicious or normal. But how we do this? I mean, since we are generating attacks, we know how they look like. We know all the specifics, and by adding the rules, we can then filter out which traffic packet was normal or malicious one.
Right. I mean, for the research purposes, this is supervised where, as you say, we have clear understanding. But the project end result is to have the OT sensor as expansion to the CERT.LV capabilities, hopefully being released also for the other of the community. But at that point, you don't have the knowledge. It's deployed in the target network, and it has to learn. How would you try to figure out that solution? Is it a hard solution, or is it an easy solution with the machine learning?
I mean, it's definitely not going to be an easy one, but I think we have the best possible setup for executing this. So we'll see how it goes. I'm not sure about the results, but I hope that we are going to achieve results that are better than the previous one, at least in the scientific community.
All right. So you mentioned also Open Caldera, and Open Caldera doesn't support IEC 104. Have you, and it's most likely yes and no, but please expand on this. Have you looked into how hard it is to expand Open Caldera with adding a new protocol? Like, is it a huge effort to add IEC 104 there to simulate attacks?
Well, unfortunately, the answer is no. I haven't looked at it. But I know that they are working on some other. They're expanding this tool and working on other protocols. I'm not sure which ones, but I hope that in some near future they will add the protocols that we are using in this research as well. I mean, the good thing is that we are also using Modbus, but since the research only started with IAC 104, we haven't got into that yet.
All right. And for sure, I mean, Open Caldera being from Mitre framework, they're more US-centric. The DNP3 is a protocol that's similar to IEC 104, but more US-related. So maybe there's some caveats there as well. Any questions? Yeah, there is one question from the audience. There was a very quick hand up, so it's very good. He was waiting for me to ask. Go ahead.
I have put few thoughts together. Humans make errors, and those industrial networks tend to be very complicated. Do you see a potential that this system can be used, that there is no malicious activity, but there is an error made by an operator?
Yeah, for sure. Sometimes, as I mentioned before, at the rule-based approach, if specified actions are whitelisted, so 9 to 5 actions by an operator are okay, for example, but if someone stays a bit longer or accidentally does something, this can trigger an alert and block something. So yes, I'm pretty confident that it would be able to detect some errors in the operators as well.
All right, any more show of hands? Right. You're currently working, Henry, on your thesis, right? But there are going to be deliverables as well. One of the first deliverables, what is the first outcome? The release of a data set, or what's going to be that?
So the goal would be that in each of these boxes there would come out some scientific publication. Well, currently we are working on a publication about threat scenario development and how we are creating the labeled dataset. And so yeah, then afterwards, how we are going to apply machine learning. That I think that's going to be another publication, and in the end, the whole IDS publication.
Right. But for the community around, so the label data set will be the first one to come out. So if you're working in the energy field and IEC 104 is your protocol, then check out what Henry is doing. Hopefully you can reach out to him during the break. All right, with this, unless there are last questions, there are none. All right, let's give a round of applause to our speakers.